Okay, so here's the big idea to start off with, is that they tell us right here, the heat absorbed in a given time by a piece of the net. Now, I'm going to call that DH. Right? And it tells us that that is the area of that piece, which we usually call DS, and then times the temperature difference function, which is given by that formula 3Z. The name for this function is capital T. So this is a given statement right here. Is that cool? Okay. All right. Now we've been asked to compute the grand total amount of heat, and the argument I would make then is that I'll do this in black. So the total amount of heat, what I'm going to do is just add up these little pieces of heat over the entire surface. And so that means I'm going to be adding up T of XYZ times ds. Because, as previously argued, that is that. Is that good?
Yeah.
Yeah.
I got to that point, but I didn't know where I'd go from there.
Oh, okay, yeah, cool. All right, very good. Well, no problem. All right, so, well, it's a matter of writing it down at this point. Now, let's see here. We've got this temperature difference function is 3Z, and it's area times that. So we're going to have double integral over the surface of 3Z ds. All right, now the way we compute scalar surface integrals is we parameterize the surface. That's step one, is parameterize the surface. So coming up here, good news, we are given a parameterization of the surface right there. All right, so we're going to just take that as given. Specifically note U and V range over the unit disk and the UV plane. But starting with that formula, now let me recopy 2U minus V. Let's see, Y is U plus 2V. And Z is U squared plus V squared. Okay, so this ds thing that we're interested in is length of capital N du dv. That's just our usual formula. Yeah, everybody good? Mm-hmm. Okay. So I'm going to have to compute capital N, which means I have to compute xu and xv. I mean, there's a whole little process there. Xu is, well, I'm going to take the partials with respect to u, and I get 2, 1, 2u. Xv, now I'm going to take the partials over here with respect to v this time, and I get minus 1, 2, 2v. Now I'm going to take the cross product of those. And so, some algebra here. So the first component, 2v minus 4u. Then I have minus 2u minus 4v. And then I have 5. Yeah? Everybody happy? Okay. All right, so that's my capital N vector, but I'm actually interested in the magnitude of that. Okay, so we've got a magnitude of capital N.
I have a question. Do you do that to make it easier on yourself, or can't you just do it?
Oh yeah, I mean, I could have written sort of magnitude of and just have the whole thing. I think I did that in the book a couple times. Yeah, sometimes I find it easier just to. I don't need to write magnitude all the way down if I'm I can just compute it in stages, in other words, and that's fine. Yeah. Okay, so the magnitude of this. Well, I'm going to have the square root of 2v minus 4u squared plus minus 2u minus 4v squared plus 5 squared, which is Gosh. Let me try to do this sort of quickly just to save on a few pixels. I'm going to have 4v squared, and then I'm going to have another 16v squared. So altogether, I've got 20v squared. Right. And then likewise, I'm going to have 16u squared and another 4u squared. So I'm going to have 20u squared. Now, let's see the cross terms. Here, the cross term is minus 16 UV. Here the cross term is plus 16 UV. So those cross terms cancel. Is that cool?
Yeah.
Okay. And then this is plus 25. Okay. So there's our magnitude. So that is my stretching factor. So all together, I have integral of 3z ds. That's don't forget z is u squared plus v squared. The stretching factor is this square root of 25 plus 20 u squared plus v squared. And then du dv. Oh, and I'm sorry, this is a double integral. Yeah. All right, now at this point, I'm already thinking polar coordinates, right? And then it's further compounded by I'm given that u and v range over the unit disk in the UV plane, right? So it really screams polar coordinates, and in polar coordinates, this integral is pretty doable.
Yeah.
Yeah. But did you want to see that part of it, or
for some reason, instead of getting a vector as an answer, I thought it was like a dot product, so I ended up adding the products of the determinant.
So there's no dot product.
Yeah, that's
right?
That's
okay.
So like I got a different integral in that. Like
okay.
That's a lot easier than.
Oh, okay, yeah, good. Okay, so everybody's happy with this integral?
Do you end up doing like a trig substitution with that?
Oh, let me think here. Maybe. That'd be one of the things you can try. It might also be able to do just a regular substitution because you're going to have some extra factors of R lying around because of the the stretching factor, the polar stretching factor in there. So you could let this be W, right? And then W prime would have just an R in it. So it might not require trig substitution. Yeah. Right. Maybe integration by parts. I don't know. Got to get into the details. Okay, it looks like everybody's happy, so let me stop this one.